out of which you see that two stages are at the beginning, first and second stages are differential amplifier. First stage is differential amplifier that is having double-ended output. Second stage is also a differential amplifier but single-ended output. Then we have in the third stage is an emitter follower. Emitter follower, is having gain of 1 and the almost 1, not exactly 1. And the last is a DC level translator or output driver. This one. Okay. This is what we are going to see in circuit form. And it is a whatever we are going to discuss is a Motorola MC1530. Normally you have seen IC 734 or something like that. You have studied. What is that? 741.
Yes, sir.
741 you have studied and used also. But this one, what we are going to discuss is of Motorola MC1530. What is there inside we'll be seeing in the next slide. Here you see that the first stage is a differential amplifier which you have discussed. The second stage is also a differential amplifier and its input. The first stage is getting input here, node 1 and 2. One is positive or non-biting input, and second input, that is 2, terminal 2 is inverting input, is getting connected here at the base of Q3, and 1 is connected to Q2. And this current source stage is here. What you can see here, we have already discussed, and RC and RC here in the form of R2 and R3. Resistance value is 7.75 kilo ohm, both the cases. Okay. As usual, IO is the bias and bias current flowing through this current source. Rather, it is current sink you can think of. And then second stage of differential amplifier is taking input from the first stage. First stage is giving two output, double-ended output, and they are connected to the two bases of this second stage differential amplifier. And you have the R7 here, which is equal to 3 kilo ohm. And here you see it is having a emitter follower with a gain of almost 1, and you have the output or buffer stage or driver stage. Okay, altogether we have 4 stages. Now we'll describe one by one what will be the input resistance and all of this operational amplifier. The first stage gain, voltage gain AB1, consists of Q2 and Q3. This Q3 is E1. With Q1 used as a current source. This Q1 is acting as a current source with its biasing resistor and diodes. As we have seen in the last class, that one diode is not sufficient, 2 diodes is used here. The differential input resistance, RID here, input resistance between this two terminal. The differential input resistance RID to the total input signal VI is 2 HI. HI is what? Input resistance of the transistor cell. Transistor cell, which is not external. Okay. Provided RS equals to 0 and HOE into RC less than equals to 0.1. This is the condition is thought of. This statement follows from the fact that since Q1 acts as a constant current, IO, this current is constant. The emitters of Q2 or Q3 are floating. So for AC analysis is concerned, do you understand that? This point you have to remember. Since a constant current, constant is not current is not affected by the input signal and its excursion and the amplification. It is not able to make any change in the current. No change means zero. You can think of zero change or no change. Okay. So for DC analysis, if IO equals to constant, then for AC analysis we can think of it is that as if it is disconnected. Okay, it is almost floating. It is not getting any ground or something like that. For small signal or AC analysis, constant current source is removed. That is, it is disconnected. Hence, the resistance between two inputs, 1 and 2 here, is HI2 of this one and HI3 of U3 equals to 2 HI. If input 2 is grounded, suppose this one is grounded, then input 1 is loaded with 2 HI. If you neglect RBB, we know what is RBB. Compared with RB prime E. RBB is what? It is base spreading. We have discussed it. Resistance of a small signal model of a BJT. So HIE will be almost equals to RB prime E equals to HFE by GM, and GM is defined as mod of IC divided by VT, where VT equals to VT is 26 millivolt at 300 K or room temperature, where use of equation, this equation has been used, and this we have I think discussed earlier. We show further in this section that IC2, IC3 and IC4 equals to IC5 equals to 0.5 milliampere. Since HFE equals to 100, we have seen earlier various tables regarding the H parameters. In that we have already seen that HFE may be equals to 100. For Q2 and Q3, the differential input resistance RID equals to 2 HI. So 2, this 2 is this 2, and this is your HFE, and this is your VT, and this is divided by IC. IC is here 0.5 milliampere. So we get a resistance, input resistance, differential input resistance 10.4 kilo ohm. Are you getting my point, Aman?
Yes, sir.
Putting this value actually we get in this equation, okay, HI. So if this resistance is too small for applied signal source, the signal source is applied where? Here one signal source may be there, maybe a mic or so, okay, a mic, another maybe here, maybe another voltage source. So this is having a resistance. We have seen source resistance RS kind of things. Here also will be a source resistance RS. So we have already discussed at the beginning of this syllabus that this input resistance of the BJT based or MOSFET based amplifier is having good input resistance because there is SiO2. But here it is less, okay, less compared to MOSFET based device amplifier. So if this compared to RS, it is less or not really high, rather, okay, the input resistance of this BJT Q2 and Q1 are not really high, very high compared to RS. Then what? Then what is the solution? What should be done. We know that there will be a loss of voltage, precious voltage picked up by this signal pickup or say transducer or sensor. Okay, so the solution for that is Darlington pair. We have seen that it is having input resistance, good input resistance, so that can be used in place of Q2 and another in place of Q3. Okay, another modification is to add matched FET. Instead of BJT, if you use FET for the first stage where you are connecting the signal source, then also another solution. So another modification is to add matched FET differential stage at the input, or preferably to fabricate an FET differential pair on the same chip with the rest of the op-amp. Rest of the op-amp may be having the BJT, other BJTs, but first is you can replace with FET based so that its input resistance is high. We know that, so and there will be no problem. Valuable signal from the source may not be lost while it is being applied to the input of the differential amplifier. Wilder has designed op-amp in National Semiconductor Corporation. The op-amp is called LM108 using super gain transistors in the input stage. Current gains of about 5,000 can be obtained at 1 microampere collective current. For this transistor, we find equation this one 1525 Hi equals to 130 mega ohm. Okay, if you have the current gain term, current gain of that is HAP, in this equation, HAP is what? Current gain, and you have the 26 millivolt, and you have the IC equals to 1 microampere. So 10 to the power minus 6 is 1 microampere. Putting this value, we get Hi equals to 130 mega ohm. Could you understand, Aman?
Yes, sir.
Which is very high in case of this amplifier. The differential input resistance of the second stage consisting of the differential pair Q4 and Q5 is 2 HIE. However, since double-ended signals are applied to Q4 and Q5, double-ended signal, one from here to the Q4, another one is from here to the Q5. To the Q5, are you getting? There the input going. So they have been tapped from the first stage. So, however, since double-ended signals are applied to Q4 and Q5, then the resistance looking into each base is half this value or HIE. This result follows from the equivalent circuit of 15.7b. We have already discussed this one, 15.7b. What is that? If the BZTs are identical, say Q2, Q3 are identical, Q4, Q5 are identical, then we have seen that it can be split into two parts, and that was discussed in figure number 15-7b. Let me show that and we'll come back to this slide later on. 15-7. Yeah, this is the 15-7b. Okay, we are talking about this one. Since it was identical, it has been split, and we have discussed and obtained the various parameters. Going back to our so which indicates that the emitter is effectively at ground potential. Emitter of both. Since it is known that HFE for transistor Q4, Q5 is about 100, then HIE equals to 10.4 by 2. 10.4 we have obtained here. Input resistance 10.4 kilo ohm we have obtained. Okay, so divide by 2 we get 5.2 kilo ohm. This resistance is effectively connected from each collector 2 of Q2 and Q3 to ground. So this resistance value, whatever we discussed, is actually connected from this point to ground. That is 5.2 kilo ohm. Here also another one. That is from here. 5.2 kilo ohm. If you consider this, and also you are doing the AC analysis, so VCC is grounded. Remember, this thing is not shown, but you have to understand for analysis of AC analysis, you have to do that. So actually 5.2K and the R2, R3, that is the collector resistance of Q2, Q3 are coming in parallel, isn't it? Aman?
Yes, sir.
So parallel combination, that is RL2 and RL3 is parallel combination of R2 parallel this 5.2 kilo ohm. So it is 7.5 kilo ohm parallel 5.2 kilo ohm gives you 3.12 kilo ohm. Okay, that is what actually effective resistance there. Now open loop voltage gain. The differential gain AD equals to AB1 is given by this equation. VO by VS. AD equals to VO by VS equals to half HFE RC by RE plus HI. This equation we have seen earlier. If you go back 15 dash 14 dash 14 we have seen already. Just let us look back. 15 dash 14 is here. This equation AD equals to differential gain equals to VO output voltage divided by VS, which comes to be half into HFE RC by RE plus HI. Okay, let us go back to the slide which we are discussing. So this equation, based on this equation, we can so the differential gain AD is given by this equation multiplied by 2. Okay, if you multiply it by 2, then basically we'll get this. Okay, this thing. Because the collector to collector output is twice the collector to ground output. Since RS equals to 0, HF equals to 100, so HI equals to this. This we have already seen, 5.2 kilo ohm. But the first stage, AB1 equals to B2 by B1. B1 is this one. B2 is this potential difference between this two terminal, output terminal of the first stage. So since you have multiplied by 2, we get this equation HFE into RC. In this case, RC is nothing but your, you can say RL2, which is nothing but the parallel combination of 7.75 with 5.2K, which gives you this value. Okay, so that's why we are writing this 3.12 divided by HI, that is 5.2, gives you gain of 60. Is it understood?
Yes, sir. Yes, sir.
See, if previous discussion is not remembered, then it will be difficult for understanding. Every discussion is followed by the other one. I mean, previous discussion should be remembered. Anyway, now for the second stage, HF equals to 100, HI equals to 5.2 kilo ohm, and the load is 7 R7. load is R7, that is 3 kilo ohm. If we neglect the loading of on Q5, see Q5, at the Q5's output you have the Q6. If that loading effect is ignored, yes, there will be loading effect because it is having some input resistance, and this is another resistance. So obviously this load resistance is going to be affected, but maybe less. Why less? That will be discussing. If you neglect the loading on Q5 of the emitter follower Q6, whose input resistance is high compared with 3 kilo ohm. See, this is taken as 3 kilo ohm, R7. But input resistance here is very high. This is a emitter follower, and emitter follower is having a input resistance. CC is the input emitter follower or not? Common collector configuration is emitter follower.
Yes.
So yeah, and you see, we have seen this table earlier also. For RL equals to TK, it was 144 kilo ohm. For other value may be different, okay? But you know, at least 144 kilo ohm is quite high compared to 3 kilo ohm. So actually, this combination of these two resistance will not be much affected. I mean, this 3 kilo ohm will not be much affected. It will persist. I mean, 3 kilo ohm will only persist. So since the second stage has single-ended output, it is only taken from here. Nothing is taken from this output. Okay, output terminal. The differential gain is given. AB2 is given as V3. V3 is the output voltage. V3 is the this node voltage, which is the base voltage of Q6, and V2 is the voltage difference between these two. Differential voltage. Remember that difference between these two voltage output terminal of first stage. So this gives you this value, half HFE R7 divided by HI. So HFE gets to 100 and R7 is 3 kilo ohm. HI is equal to 5.2 kilo ohm. So kilo gets cancelled and you get this value. Minus 28.9 is the gain. Second stage gain. For the emitter follower, AV3 equals to almost equals to 1. We know it is a emitter follower, so its gain cannot be more than 1, more than unity, rather it is always less than unity or very closer to unity. The output stage uses voltage shunt feedback because of R9 here and R10. From equation 15-1, which we have already seen, AB4 4 stage gain is equal to R10 by R3 minus of R10 by R3, which is going to be minus 5. Actually, putting the values of R10, which is equals to 30K, and R9, which is equals to 6K. 6 kilo. Is it understood, Aman?
Yes, sir.
Hence, the overall op-amp gain, hence overall op-amp differential voltage gain is multiplication of those gains of the, and it is nothing but 8,670. Note that node 1 and 2 are non-inverting. That we have seen. This is non-inverting. This is inverting input terminals of the op-amp. See, you can observe that in IC 741, how many nodes terminals were there? Pins? Pins 8. How many here you are seeing? You are seeing at least 10 shown here in this diagram, isn't it?
Yes, sir.
Now DC analysis. we'll try to find out. DC analysis is done mainly for finding out the DC current or DC voltage at different terminals. Okay, so we'll analyze this and see where, in which voltage and which node, what is the voltage, DC voltage. It is necessary to know the DC currents and voltage of the circuit to obtain the open loop gain and the differential input resistors, and to understand the operation of the level translator output stage. Okay, so let's start with the current source Q1. Q1 is the current source. We have already known. We assume that all base currents can be neglected. We are assuming that base current is so small that we are neglecting compared to IC and IE. And VBE is taken as 0.7 volt. It is the case for any silicon, BJT. So this assumption is not faulty, or it is correct assumption. The DC voltage VBN1, base voltage DC VBN1. N is the neutral. See, it is having positive as well as negative supply. Positive here plus 6 volt, negative minus 6 volt VEE, and neutral is, or you can say 0 is N is neutral point. So with respect to neutral point, VBN1 is calculated as minus VEE from this side plus 2 into 0.7, because you have the two diodes. This is the voltage, and then it is going to act as a potential divider, voltage divider. So R5, R5 this here multiplied, divided by R4. It is something like this. Here a resistance, and this is your node N, and you have R5 here, and you have R4, and you have the some potential. Potential is nothing but that is minus 6 volt plus 2, and diode drop. Diode drop is 0.7 volt. Are you getting? So what will be the voltage over here? And this voltage is nothing but what? Base of Q1, isn't it?
Yes.
Base of Q1, that is it is denoted as VBN1, base to N. So this is calculated to be this one, minus 3.14 volt. Others are there. Harsh Tripathi, are you there? Harsh Tripathi, Pratham, Bushra. Nobody. Good. So now IO is this current, constant current sunk by the current source Q1, equals to I1, because we have taken base current as very negligible compared to collector current and emitter current. So IO, collector current, almost equals to emitter current I1, which can be obtained as 0.99 milliampere. Putting the values here, VEE plus VBN1 minus 0.7 volt. This is the difference between this point. Is nothing but VBE of this BJT. Okay, so we get 0.99 milliampere. If it is assumed that the integrated transistor Q1 and Q2 and Q3 are identical, 1/2 of I1 that is this current, will flow through each, that is IC2 and another one is IC3, this one and this one, and hence is half of this value, half of this value. Is it understood?
Yes, sir.
Sorry. So the DC voltage of the base of Q4 or Q5, the DC voltage of the base means this voltage and this voltage we have to find out. So we can look at from here to VCC and you can find out that. So VBN4 equals to VBN5 equals to VCC minus IC3 R3. See, IC3 is this current, R3 is this current. So there will be voltage drop, I mean, in this resistor, and that drop, I mean, VCC minus this voltage is actually the base voltage of Q5. Same will be in this case also will be same R2, because R2 and R3 value is same, and current IC2 and IC3 is also same, isn't it? So will you not get this value 2.18 volt?
Yes, sir, we will.
Both will be same base voltage of Q5 and Q4, Q5 and Q4. The DC voltage at the common emitter of Q4 and Q5, and this point is talking about common emitter of these two is VEN4. This emitter to neutral point, this point. Okay, VEN4 means that. So VBN4, I mean to say base to neutral, what we have already got, minus BB4, potential difference between these two. Okay, these two is nothing but this 1.48 volt we get. Okay, so both is same, I mean Q5, Q4, so both BEN 4 and 5 will be same, and hence current R6, current I6 flowing through this resistor R6 is potential of this point, I mean, and this point, difference between this potential difference between this two, this point divided by R6 gives you 0.986 milliampere. Is it understood, Pratham? Pratham is not there. Aman?
Yes, sir, understood.
Nothing. It's just potential difference divided by the resistance. Simple calculation. Now, since I6 equals to IC4 plus IC5. See, IC4 is this one, IC5 is this one, flowing through the collector of Q4 and Q5. Yeah. So 2 IC5 you can write, okay, because both are same. We are thinking that Q4 and Q5 are identical resistors, and at the base also the same voltage is there, same amount of voltage, that is 2.18 volt, 2.19 volt. So obviously currents will be same. Then IC5 is going to be 0.493 and the base voltage of Q6, which equals the collector of voltage V3, this one of Q5 is this. Is it understood? BBN6. BN6
Yes, sir.
equals to BCN5 equals to BCC minus IC5 into R7, that is 3 kilo ohm. Hence we get this term. DC analysis is understood up to this point.
Yes, understood.
So we are calculating the voltage of different nodes and also current. The output V4 of the emitter follower is this one. V4 is this one, this point. V4 is EN6 emitter to neutral 6, that is BBN6 minus this voltage. We know that BBN6 is 4.52 minus BB6 is 0.7, and hence it is this. Yes, this one also understood. Come on.
Yes, sir.
Going further, the output stage, and the last stage provides the level translation and a symmetrical output swing with respect to ground. When the differential input voltage V1 is 0, this is differential input voltage is 0, the output voltage VO should be 0. Of course, due to the mismatch of VBE and HFE, there will be some non-zero output voltage. We call it offset voltage, output offset voltage. We have defined that thing earlier. Yes or no?
Yes, sir.
The voltage VEN6 is 3.82 volt. Must be reduced to 0 at the amplifier output while DC coupling is maintained. I mean to say, once here it is 3.582 volt and here it is 0 volt, VO equals to 0 volt. Obviously, it has to be reduced to 0 by this thing. Okay. If you don't want to get output voltage, DC voltage, we shall now demonstrate that this level translation can be accomplished with the circuit parameter values in figure 15-11, which is this figure only. Note that Q7 is biased. Q7, this one, is biased by D3. D3 is the diode 3, biased toward that. We know the voltage across this diode is 0.7 volt. Remember? Yes or no?
Yes, sir.
And this one's BE is also to be 0.7 volt, so it is properly biased. There is not a drop anywhere. So we find that IC7, this current flowing at the collector of Q7 is almost equals to I8. See, I8 is this current flowing through R8. This is R8. Okay, this is a point, neutral point, and the I8 is flowing in this direction. That is, you can say that. So BBE minus BEE, the BEE, that is minus 6 volt, and D3 is having 0.7 volt. So actually we get this amount of current, IC7, this current. See, there is no current flowing through this because it is reverse bias. It is negative voltage. This side is positive. Okay, or you can say 0, whatever is, but drop will be 0.7 volt only across this. So all current flowing through this as a base current, which may be equal to this one only, because there is no other way to go the current. This side also you have the reverse biased case. This is more negative. Emitter side is, cathode side is more negative. Some current will flow, that is equals to I7 equals to I8. I7 equals to I8, and that is IC7 equals to I8. This current and this current. The voltage from the base of Q8. This is the Q8. That is BBN 8, base to neutral point 8 is BBE 8, BE 8, potential difference between these 2.7, of course, and D4, another 0.7 here. This is 0.7, this is 0.7, and here it is minus 6 volt. So you get BBN 8 equals to minus 4.6. And the currents in R9 and R10 are R9. This current in this direction is the potential here, that is BEN 6, emitter of Q6, and BBN 8 here, divided by R9, which is 6K, gives you 1.40 milliampere. And once you get this current I9, and what will be the I10? So I7 is coming in this direction. So I7 minus I9 equals to I10. This is understood?
Yes, sir.
That will be equal to 0.16 milliampere. Finally, the DC output voltage is VO here, or you can think of here, because same thing has been placed here as BBN 8 base to neutral 8 plus I10 R10. I10, this is the I10 and R10. This 2 voltage is the VO. So it's going to be, after multiplication of I10, which we have got earlier, and R10 is 30K, hence we get 0.20 volt. So common mode voltage swing, that is whatever we are discussing was initially was the differential voltage gain and all, then followed by TC analysis, which means node voltages and currents, etc. Now for common mode, if IC, on the other hand, if ICAM becomes more negative than then BBN1, BBN2 equals to this voltage, then the collector of P1 will become forward biased, and this will result in a abnormal operation. Therefore, when the power supplies are plus minus 6 volt, the common mode voltage swing for this amplifier should be not should not exceed plus minus 2 volt maximum. Now, pin diagram of IC 741 you have discussed. You all know that you have 8 pins. You have used this also. The first pin number 1 is called offset null pin, and pin 2 is inverting or minus pin, and pin 3 is non-inverting or plus. Sometimes in the symbol plus sign is always given minus to indicate inverting and non-inverting. The negative supply is given here, like BEE or BSS, minus BSS, minus BCC. And pin number 8 is null offset, and pin 6 is output voltage, this one. In this case, it was pin number 5. Okay, so it's a different chip, so don't expect same. Number 6. Pin number 7 is VCC. Pin number 7 is VCC. In this case, what is the pin? Pin number 6. Okay, and pin 8 is not connected anywhere. Okay, so unused, you can say. So we have only 1 or 2 minutes, so we'll discuss about the stop discussion for the next class. Now, operational amplifier, whatever you have come across earlier, 741. Now we have seen MC 15. What is that? 15. Motorola. What is the number? Plus 1508 or what? 30. 1530. 1530. But internal of this we studied. Externally, you know, IC 74, you know. So now we'll be utilizing operational amplifier in general. Whether it will be this one or this one doesn't matter. Its general characteristic is same. Whatever we have discussed at the beginning, its input resistance should be high impedance, and output impedance should be very less or closer to 0. Gain should be as high as possible. CMR should be as high as possible or infinite. Common mode rejection ratio should be as high as possible or infinite, but it is not possible because you have the definite common mode gain. So all those things keeping in mind will be now symbolizing operational amplifier, and we'll discuss its application in various cases. Okay, that will be the next class. Now let me stop here. And about Tripathi, are you there? Harsh Tripathi? Harsh Tripathi, are you there? Pratham? Harsh Tripathi is not there. Pratham is not there. Then Aman, when we will go for the one class I missed? We have to take that class. You do one thing and discuss with others and decide. We may be taking in this week whenever you are free, so that I have to sometimes take leave. Then if I take leave and that leave class is also not taken, so there will be a shortage of classes. Possibly may not be able to cover it up before 20th of April. So you plan and inform me. Okay.
Okay, sir.
Let us leave the class and you take other classes.